Okay, this is problem 1-3. Part A asks for the velocity of the ball just after it first bounces off the plane at P1. So it's asking for a vector. So we can set this line right here to be our new baseline at h equals 0, where the plane P1 is. That just makes your job easier. We're going to use the conservation of energy. So that way we can just account for this use of energy as the ball moves through the gravitational field and the energy is converted to kinetic energy, rather than having to also account for this. So E equals U plus K, that's total energy. We're just going to set gravitational potential energy equal to kinetic energy. And this velocity vector is going to look like this. It's going to be horizontally to the right when it bounces. And so we know that the velocity in the y direction is 0. So solving for v, we get, multiply that by 2. V equals the square root of 2gh. Okay, and it moves to the right, horizontally to the right. Okay, so part B. Asks for the time the ball is in flight between points P1 and P2. Well, we can use some kinematics in this and a little geometry. So looking at this shape right here, this length of L, the path that it takes between P1 and P2, we can divide this into x and y components. Okay, so I'm going to do that in my paper here. It's ugly. Let's say this is 45 degrees, and this is L, just like they said, L and 45 degrees. That means that this is a 45-45 right triangle. So this is L over rad 2, and this is L over rad 2. So we know that the velocity is constant in the x direction, and we can first solve for the velocity in the x direction over this distance. So let's do d equals vt. This is vx. The distance over the x direction is L over rad 2, which equals velocity, the horizontal velocity, times time. We know what the horizontal velocity is. We found it in part A, so I'm going to plug that in. L over rad 2 equals rad 2 gh times t. Okay, so during the same time t, the ball travels the same distance vertically. During t, it's going to go the same distance down as it does sideways. So we can use kinematics and this equation. For the y, we're going to do distance equals velocity in the y times time plus 1/2 a t squared. There is no initial height. We're just going to start from 0. So there's also no velocity in the y direction. It's purely horizontal. And so we're left with distance equals 1/2 a t squared. And the distance we already know is L over rad 2, which equals 1/2 a t squared. And a is just gravity. The ball, as it falls down, all it's bringing it downward is gravity. There's no velocity bringing it down the y direction. That's why we cancel that out. All that's bringing the ball down as it hit here is gravity. So 1/2 gt squared equals L over rad 2. So both this equation for the y and this equation for the x, we can set them equal to each other, both equal to L over rad 2. So we're going to set 1/2 gt squared equal to this. Alright, and we can solve for time. So I'm going to do that for you. The t gets canceled out, and you have rad 2 gh equals 1/2 gt. T equals 2 rad 2 gh all over g. We can bring this g into the radical by squaring it. So t equals 2 gh over g squared. And that's just going to equal, we're going to bring this 2 back into the radical, and we have 2 times 4 times h times g all over g squared. And that's going to give us our final answer of rad 8h over g. Basically, we just try to get this under the radical just so we could have a nice neat answer of time by squaring this and squaring that and just doing the algebra. Okay, so that was part B. For part C, what they want is a distance L along the plane from P1 to P2. So all you have to do is just substitute what we found for t into one of the L equations we had earlier. So just pick any one. I'm going to go with L over rad 2 equals 2 rad 2 gh times 2 rad 2 gh all over g. This is what we had found earlier. We had found that L over rad 2 equals rad 2 gh times time. That's what we had for time. It's our t, and that was from our original equation. And you just combine it, and you just combine this part. And all you get is L equals, well, the g's end up canceling out, and you just have L equals 4 rad 2 h. So we found what the distance of L was in relationship to the height, which is perfect, between these 2 points right here. Okay. Part D asks for the speed of the ball just before it strikes a plane at P2. So we're going to use the conservation of energy again, but this time we're going to have a new baseline at P over 2. We're going to start from the beginning. This is our new baseline. So we're going to use conservation of energy again, and it's going to look like this. So potential energy is going to equal kinetic energy. That's our gravitational potential energy, which equals our kinetic energy. Basically, as a ball falls down through a gravitational field, it converts into kinetic energy, and through the conservation of energy, the law that energy must be conserved in this elastic equation is that these two will end up equaling each other. So this is going to be mgh, but our height is not just h now. Our height is going to be h plus L over rad 2. That's, we have to account for this height along with this height. That's going to equal our kinetic energy, which is 1/2 mv squared. And all you need to do is solve for v. It's just this easy because really all the ball does is it just, from here it just bounces. Gravity just acts on it, and there's just kinetic energy in that one expression. So just solve for v now, and so let's do that. So we're going to multiply, so we can cancel out an m and multiply by 2. So 2gh plus L over rad 2 equals v squared, and v is just going to equal the square root of 2g times h plus L over rad 2. And that's your velocity at P2.